Morning, everybody. All right, so here's where things take a turn for the weird because this is a class about stars, galaxies, and cosmology, and there are two big issues in cosmology that are as yet unsolved mysteries, right? That are still issues that we haven't entirely figured out how to resolve yet, that influence the whole universe, and have influenced the universe from the Big Bang to today and will into the future. Um, Big mysteries that we've figured out are mysteries over the last 100 years, and that people are still working on today. These are still very hot topics today that people are trying to figure out. And so we're going to be hearing about these issues for the rest of our lives because hopefully people are going to keep on working on them and make some headway on answering them over the course of our lifetimes. So this is a very present issue. I'm dancing around it. I've danced around it long enough. These two issues are what are called dark matter and dark energy. And dark matter and dark energy are two different things, two separate mysteries, but we're going to talk about them both in this lecture. So, what the heck is dark matter? Why are we talking about this? Well, okay, let's think about our galaxy, right? What is our galaxy made of? Our galaxy is made of mostly stars and gas, right? You've got main sequence stars and all the giants and the white dwarfs, and also neutron stars and black holes, all right? So those, I'll just lump those all together and call them stars. And then you've got the gas of the interstellar medium, right? The gas that's floating around in between the stars, the ISM, the interstellar medium, and as well as nebula and supernova remnants and planetary nebula and all that gas. So if we lump all that together, what's the Milky Way made of? Stars and gas. And if you add all that up, if you look around our galaxy and if you try to add up all the stars and all the gas in the whole Milky Way galaxy, that all adds up to be about 400 billion solar masses. The range is somewhere between 200 and 400 billion, but a lot of the most recent measurements lean toward the higher end. So let's say it's about 400 billion solar masses, which is a lot of stuff, right? 400 billion times the mass of the sun is a lot of stuff, but then again, we're talking about the whole galaxy, right? Our whole entire galaxy. But if you figure out how much gravity there is, or if you measure how strong the gravitational pull of our galaxy is, that actually adds up to be somewhere between 600 and 1,000 billion solar masses. And it's probably in the middle. It's probably, let's say, about 800 billion solar masses. So what's up? Those two numbers do not agree, right? When you look around our galaxy, using telescopes and add up all the stars and gas, it looks like our galaxy has 400 billion solar masses worth of mass. And yet our galaxy has a gravitational pull as if it were made of 800 billion solar masses. So one of two things is going on here. Either we don't understand how gravity works, which is why gravity is pulling stronger than we think it should, or maybe there's just a lot of extra mass in our galaxy that we haven't accounted for yet. Right? Neither of these is a very pleasant solution, right? Either we don't understand how gravity works, or there's a lot of mass in our galaxy that we haven't seen in our telescopes yet. I don't like either of these, and yet one of these must be what's going on here. How can we resolve this? What's the right answer? Well, let's get back to the top of the slide here where I say, oh, how do we figure out the weight of our galaxy? How do we figure out what the total mass exerting gravity in our galaxy is? Well, to do that, use Doppler shift, right? Use the Doppler shift of light. If you've got a spiral galaxy like ours, and if you look around the galaxy, you can look at, say, let's say you've got this spiral galaxy and the whole disk is rotating in one direction, which is in this cartoon counterclockwise, right? And if you're looking at a galaxy, you can look at the stars rather, look at the stars on this side of the galaxy. If these stars are orbiting toward us, then that starlight is going to be a little bit blue shifted. And therefore, all of the emission lines or absorption lines, the light from all these stars will be blue shifted. If you look at the stars in the middle of the galaxy, well, it's not moving toward us or away from us. And so that light is going to be right where you expect it in the lab frame, in the lab wavelength. And then if you look over here on the right side, these stars are orbiting away from us, and so their light is going to be redshifted. And so you'd see, so depending on where you look in the galaxy, this starlight will be a little blue shifted, this starlight will be a little red shifted, this will be right in the middle. By looking at that Doppler shift, you can figure out how fast these stars are orbiting. Why are those stars orbiting around the galaxy? Because the mass of the galaxy is holding onto those stars, right? The total mass of this galaxy is pulling these stars into their orbits around the galaxy, and therefore, the faster these stars are orbiting, well, why are those stars orbiting faster? Because they're being pulled with a stronger gravitational pull. Why are they being pulled by a stronger gravitational pull? Because there's more mass in the galaxy. Right? We can weigh a galaxy. We can figure out what's the total mass of a galaxy just by taking these stars at the edge of the galaxy and saying, well, how fast are they orbiting? The faster they're moving, the more mass there must be in the galaxy. All right? And so when you look at our galaxy, this graph here is a graph of the orbital speed of, in this case, the planets in our solar system. Right? Mercury is the closest one. Pluto is farthest from the sun. I just called them planets. Is Pluto a planet? That's a debate for another day. But in our galaxy, right, the farther a planet is from the sun, the weaker the gravitational pull of the sun is on that star, or planet, sorry. And therefore, if the gravitational pull on the planet is weaker, it orbits around the sun slower. Right? So you would expect that the stars in our galaxy would basically would be the same, right? The stars near the center of the galaxy would be orbiting faster, and then as you get further and further out, the stars are orbiting slower, until you get to the stars at the very edge of the galactic disk, and they're going to be orbiting, they're really far from the mass of the galaxy, so they're going to be orbiting the slowest, right? These stars would orbit faster, these stars would orbit slower. That's what we expected about 100 years ago when people started making these measurements. Here's what it actually looks like. Here's what the rotation curve, that's what this graph is called, the rotation curve of the Milky Way looks like, right? These stars, well, the stars near the very center, the stars in the galactic bulge are moving kind of slow because they're at the very center of the galaxy, so there's not a lot of mass in the very center to be pulling things around. And as you get further and further out into the bulge, these stars move faster, and then once you leave the bulge of the galaxy and get out into the disk, it doesn't slow down. It's pretty flat. What's up there? Right? We expected that as the stars were getting further from the center of the galaxy, they'd be slowing down, and they're not. In fact, when you look at this, right, these stars here at the very edge of the galaxy are traveling the same speed around the galaxy as the stars near the sun. These stars out here, if you do the math, if you do the physics, these stars are moving so fast that they're actually moving faster than what you think the escape speed is. Those stars at the edge of the galaxy should be flying away from our galaxy. They should be blasting their way away from our galaxy and shooting out into space. And they're not. They're stuck orbiting around the galaxy. Why? Because there's more gravity pulling those stars into faster orbits than what we expect. This was the first measurement that made people realize, oh, something's up in our galaxy, that there's more mass, that there's more matter in our galaxy than what we can see. Or the other option is maybe we just don't know how gravity works. This was the first piece of evidence that said something is up in galaxies. But you know what? If you have a healthy skepticism, measuring our galaxy is tough because we're inside of our galaxy. We're stuck here in the middle of the Milky Way, and we're looking out into the galaxy, trying to make measurements about the far side of the galaxy when you're stuck inside the galaxy and you've got all this interstellar medium blocking your view. That can be tough. And so there was some astronomers that said, okay, maybe these are just bad measurements. Maybe this graph is wrong. Maybe we're just making these speed measurements incorrectly. Let's look at other galaxies. Let's look at other galaxies, and when you look at another galaxy, you can actually look at it from the outside, and it'll look like this, and you can make sure, okay, I'm measuring the speed over here correctly, I'm measuring the speed over here correctly. I bet if we look at other spiral galaxies, their rotation curves will look like this, they'll look like what we expect, and they won't look like this nonsense. I bet this is just bad science. Nope, it's happening to all of them, apparently. All of these spiral galaxies, and I mean, this is just a handful of, for example, but these are not anomalies. All of the spiral galaxies have these flat rotation curves where the stars don't slow down. They just keep on going at the same speed, regardless of distance. Which means if they're all moving faster, they're being pulled by a stronger gravitational pull than what we can explain from the visible stars and gas that we can directly observe in those galaxies. So again, now we got two lines of evidence, right? The rotation, or we'll fold them together into one big line of evidence, right? All of these spiral galaxies are rotating way faster than they should. Around this same time, other astronomers were looking at galaxy clusters. Right? One of the big discoveries made by a guy named Fritz Zwicky. This is him. I just love this photo. It's hilarious. Him in his office trying to give a lecture to a photographer, and the photographer captured him, mid-sentence trying to make a good point. Here's my little cartoon here. All right, so here we've got some, let's say these are ellipticals and these are some spirals, and in a galaxy cluster, all of these galaxies are gravitationally bound to each other, right? There's enough gravity in these clusters to hold the galaxies in orbit around each other. And what Zwicky measured is that these galaxies are moving way too fast. These galaxies are moving so fast that this cluster should fly apart. Those galaxies are humming along so fast that they should just blast away from each other. The whole cluster should fly apart, and all of those galaxies should be off on their own. And in fact, given that there's been so much time in the universe so far, these galaxies should have flown apart from each other a long, long, long time ago. But they haven't. These galaxies are still stuck, orbiting around each other, because there's extra mass or extra gravity holding these galaxies in orbit around each other, and way more gravity than you can explain from the stars and gas that you can actually see, the visible matter. So apparently this extra gravity is it's happening inside of galaxies, and it's happening in between galaxies. So that's piece of evidence number 2. But you know what? People said, you're treating gravity as if it works the way Newton says it does, right? You're treating gravity as if it is an invisible force pulling stars and galaxies around each other. And I'll say, well, yeah, that is pretty much what I was just saying a second ago. But we know that's not right? We know gravity actually works the way Einstein says it does, right? Gravity is the curvature of space-time around massive objects. So maybe the solution is let's just get a better handle on general relativity. Maybe that'll explain why there's this extra gravity, more gravity than you expect. All right? How can we do that? How can we use general relativity to measure the mass of things? And we can do it through gravitational lensing, right? When you look at galaxies, a galaxy has a lot of mass. A galaxy can bend light around it. And so we've seen this cartoon before, right? We saw this when we were talking about general relativity and black holes earlier, right? If you've got, here's Earth, if you've got a mass in the foreground and a mass in the background, and that mass in the background is giving off light, then that light is going to shine away from the real object, and that light can bend through the curved space-time of the massive object in the foreground and shine on Earth. And so what we see on Earth is an image, an artificial image. I shouldn't say artificial. It's not like it's man-made, but you get an unrealistic image, right? It looks as if the light is coming from over here. From Earth's point of view, it looks like the light is coming from over here. So you're getting an image of the real object, but it's in the wrong place, right? This image is over here, and then if this light bends around here, then it looks like over here, right? So a lot of times what you get with gravitational lensing is more than one image. You'll see, like, you'll from here on Earth, you'll see an image of a galaxy over here and an image of a galaxy over here, but the galaxy is actually over here. Well, that's what we're seeing here, right? These yellow things are elliptical galaxies in the foreground, and the blue light is the blue light from a bluer galaxy bending around the foreground galaxy and then creating an image here on Earth, so that that galaxy there, that little blue arc here and this big blue arc here, that's the same galaxy. That's a blue galaxy where, some of the light got bent this direction, some of the light got bent this direction, but really, where's the galaxy? It's behind the yellow galaxy, in the way that the blue object here is behind the yellow object, right? You see this all over the sky, right? Whenever you see really high mass galaxies or galaxy clusters, when there's a lot of mass, that can bend a lot of light, and then you get these little curves, right? These little arcs of light from a galaxy in the background getting bent by the galaxy in the foreground and then shining on Earth. And it looks distorted, right? The galaxy doesn't actually look like an arc, but the light got bent in an arc the way that light bends through a lens. That's why it's called gravitational lensing, because the light is being focused onto Earth the way that a lens focuses light. The more the light is bent, the more mass the object in the foreground must have. So here we have a different way. Here we have a different way of measuring the mass of a galaxy or a galaxy cluster by looking at how much does that galaxy in the foreground distort the image of the galaxies and objects in the background. It's a geometry problem, basically. You've got Earth, you've got this cluster in the foreground, you've got these real galaxies or this real galaxy in the background, and you want to measure, well, how much is that cluster in the foreground bending the light? And it's a little bit of trigonometry, it's a little bit of geometry, where you say, well, if I know the distance from Earth to this cluster, and if I know the distance from Earth to the galaxy in the background, right? If I know these lengths, I can figure out, I can do the bending in the other direction and figure out how much this cluster is bending the light. And if I measure how strongly that cluster is bending the light, I can do the complicated general relativity math, bending four-dimensional space-time, to say, well, how much mass is there, right? I can figure out how much mass there must be in this cluster by figuring out how much that mass is bending the space-time around it. How do I figure out these distances? Hubble's law, right? Measure the redshift to this cluster. Measure the redshift to the background galaxy. The redshift will tell you if you have Hubble's law, and if you have a good value for the Hubble constant, you can figure out the distance, right? It's a strong tool. Hubble's law is a strong tool. And so that's what we do. Measure the distances, measure the mass. Lo and behold, what do you get? You get that there is way more mass in these galaxies than what we can see in stars. Right? Here is a rich cluster of galaxies, right? The local group, our galaxy cluster, it's a small cluster, right? The local group is a small cluster of galaxies. Abell 2218 is what you call a rich cluster of galaxies. It has hundreds of galaxies all orbiting around each other, right? That's all the yellow stuff here, right? These are all galaxies all orbiting around each other in the foreground. What's the stuff in the background? All the bent stuff, right? All these little arcs, this red one here, this blue one here, this big bright blue one right here. All of these little arcs are the images of background far away galaxies bent by the curved space-time they're passing through before the light shines here on Earth. And so by measuring all these little arcs, you can say, well, how much mass must there be to curve space-time the way we see it? And you come up with a lot more mass than all the stars that we can see. So again, this is line of evidence number 3. Right? Gravitational lensing is happening a lot stronger than you can explain with just the normal matter, stars and gas. But that doesn't solve the mystery, right? Which is it? What's the problem? Is the problem that we don't understand gravity, or is the problem that there's invisible mass? Up to this point in the lecture, the answer is we don't know yet. Until this picture was taken. Right? This set of images was taken in 2006. This is what's called the bullet cluster. It's actually 2 clusters of galaxies. So you've got a cluster of galaxies here and a cluster of galaxies here, and they actually flew through each other a while ago. Right? How do we know? This cluster of galaxies is moving this way, so the cluster on the left is moving to the left, the cluster on the right is moving to the right, so actually this smaller cluster used to be on the left side, the large cluster used to be on the right side, and then they flew through each other and switched places. When that happened, the galaxies, I should say, the stars, just flew past each other. Right? There probably weren't a lot of collisions. There's a lot of empty space out there in space. And so when 2 clusters fly through each other, there's not a lot of it's not like stars are crashing into stars. The galaxies just kind of fly past each other. But the gas doesn't. Right? The gas, when these 2 galaxies flew through each other, the gas from the larger galaxy and the gas from the smaller galaxy smashed in together. Those 2 halos of gas smushed together and came to a stop in the middle. That's the pink stuff. The pink light in this image is actually X-ray emission, because when you've got 2 clusters of galaxies worth of hydrogen and it all smushes together, what happens to gas when you compress it? It heats up. So these 2 giant clusters of galaxies, all that gas collides in the middle, all that gas compresses, it gets denser, it heats up, and it heats up enough to give off some X-rays. This system is a big deal. Like, I don't want to undersell this. When these pictures were taken, this was a big deal, because the problem with taking pictures like this is that the problem with galaxy clusters most of the time is that the stars and the gas are all mixed together. Right? How much gas is there? I don't know. All I'm seeing is a bunch of stars. And you can try and measure the gas, but the measurements, gas is not as bright as stars. Right? Stars are a lot brighter than gas, but there's still gas floating around in between the stars. There's gas floating around in between the galaxies inside of clusters. But how much gas is there total in this cluster? You can try to make that measurement. You can try to see the emission and the absorption from the intergalactic medium. That's the name for it. The gas that floats around in between the galaxies is called the intergalactic medium. You can try and do it. It's tough, right? You can't just look in this picture and say, well, there's clearly this much gas. You can do that with stars because the stars are really bright, and you can measure the brightness of these galaxies, and you can get a good measure for how many stars there must be in there. Hard to do with the gas, though. Here, though, we know how much gas there is because it's giving off X-rays. Look at how much gas there is. We've got a good measure for the gas. So this system is special because basically the stars and the gas are not mixed together. The stars and the gas got siphoned away from each other so that over here, the yellow light that we're seeing in this picture is stars, right? What you're seeing of these galaxies in this cluster is the stars. Over here, you're seeing the stars. Where's the gas? It all got stuck in the middle. So now we have a really special situation where we know how many stars there are. That's the yellow light. We know how much gas there is. It's the pink light. Here's the thing. Right? So, I'll get there in a second. Add that all up. Add up the stars. Add up the gas. What do you notice? There is more gas in this system than there are stars. I'm going to say that again. The total mass of all this gas in the middle is much, much greater than all of the mass of stars over here and over here. So, if the normal matter, if all of the mass that we can see is what's causing the gravity, then the gravity should be concentrated with the gas, right? There's more gas than there is stars. So the visible mass is concentrated with the gas over here, and not here, and not here. Where's the gravitational lensing happening? That's the blue areas, right? Most of the gravitational lensing is happening over here and over here. This is the smoking gun, right? This is the smoking gun that tells you, how do we solve this mystery? Do we just not understand how gravity works? Maybe gravity is just stronger than we expect. No, because if gravity just doesn't work the way we think it does, then the gravity would be concentrated with the gas because there's more gas than there is stars. Where's the gravity actually concentrated? The gravity is actually concentrated in the blue areas. What's creating all of this gravity? Well, it can't be stars. There's not enough stars. And it can't be gas because the gas isn't here. It's here. There must be something else. Right? Because the mass, the actual mass that is actually lensing the light from galaxies in the background is the blue blobs. And that gravitational lensing is not caused by stars, and it's not caused by gas. There has to be some extra mass here that is causing the gravitational lensing, but it's not anything we can see in our telescopes. This is why it's called dark matter. Right? Now, this is confusing, right? Because you'd think it's called dark matter. That means it's black, right? No. If the dark matter were black, it would absorb light. We would see it in our telescopes. the way dark nebula, right? We call this extra mass. This extra mass that is causing stars and galaxies to move faster, the extra mass that is causing extra gravitational lensing. This dark matter is what? What is it? It is extra mass inside of galaxies and inside galaxy clusters, but we can't see it in our telescopes. Not because it's black. This is where the name is, it's not a great name. I'm gonna admit that. Calling it dark matter is not a great name. Because dark, you'd think it's dark, it's black. No, it's invisible. It is transparent, right? The dark matter does not give off light, but also the dark matter does not absorb light, because if the dark matter absorbed light, we would see that in our telescopes. The dark matter is transparent. It's see-through. The light passes through the dark matter unabsorbed. So it's hidden from us. We call it dark matter because we're in the dark, right? We call it dark matter because we, the humans, we, the scientists, we're in the dark about what this stuff is. That's why calling it dark matter is sort of it's a placeholder, right? We call it dark matter because we don't know what to call it. But we know it's real because you see it everywhere. Right? You see it inside of galaxies and you see it in between galaxies. And also, apparently, it's been there since the beginning of the universe. This set of pictures is a simulation. Some scientists trying to simulate how the universe has evolved from the Big Bang to today. All right. So simulating the entire universe would be a huge job, and it would require an insane amount of computer time. So the nice thing is that the universe is pretty much the same in all directions, right? The universe is homogeneous and isotropic, so we don't need to simulate the whole universe. We're just going to take one chunk of the universe. Like, let's take one cube out of the universe and let's experiment with that, and we'll just assume that this cube is representative of the whole universe. All right? So when the universe was only 500 million years old, let's take a cube that's 13 million light years on a side, and shortly after the Big Bang, the universe was mostly smooth. It was still very hot, and the gas was cooling off, and the universe was expanding, right? As the universe expands, right, as the expansion of space-time happens, billions and billions of years, that cube is going to get bigger and bigger and bigger, right? This cube of space expands to get bigger and bigger, but also gravity is trying to pull all the gas together. And so as gravity tries to cause that gas to clump up and collapse, this cube of space in our simulation gets clumpy. It gets clumpy, and then those clumps collapse even further and collapse even further into bigger and bigger lumps, and then each of those lumps of gas collapses and forms the very first generation of stars and galaxies. So by the time you get to a universe that is 13.7 billion years old, that cube has expanded to be 140 million light years on a side, and then each of these big clumps is a cluster of galaxies, right? Each of these little lumps, each of these little bright spots in this simulation is a galaxy, and each of these big clumps is a cluster of galaxies. I said it before and I'll say it again. The history and the evolution of our universe is a fight between two forces. Expansion is wanting to carry everything apart, and gravity is wanting to pull everything together. And so this is how this simulation is showing how those two forces fight with each other. Expansion is making space bigger and carrying gas, stars, galaxies apart, but then gravity wants to pull things together into galaxies and clusters of galaxies. Okay? Here's the problem. If you do the simulation with just visible matter. If you do this simulation with just normal gas, the hydrogen and the helium that came out of the Big Bang, we'll get more to that in the next lecture, but it's not enough. If you make this simulation where the gas you start out with is just normal protons, neutrons, and electrons, right? The stuff that we understand, the stuff that we're familiar with, the stuff that makes up atoms and molecules and visible matter, stars in the ISM, it's not enough mass, right? There isn't enough mass, there isn't enough gravity to cause the gas to clump up into big clumps, and then those big clumps collapse and form big galaxies. If our universe was only made of normal matter, protons, neutrons, and electrons, hydrogen, helium, the periodic table, the standard model of particle physics. Remember in the structure of matter lecture, right? Talking about the standard model of particle physics, right? The standard model of particle physics is, I'm going to call it normal matter, right? The stuff we understand because we can see it, either in particle detectors or in telescopes. It's not enough to pull the gas to form large galaxies. We wouldn't be here. The Milky Way is a big galaxy. Our galaxy wouldn't be here if there was only normal matter. So what do? Go back to the simulation. Let's say, okay, let's start over again, but this time let's add a little bit of extra dark matter. And that extra dark matter creates a little bit of extra gravity, and with that extra gravity, you start forming bigger galaxies. And then, but still not enough, right? Still not enough big galaxies to match the number of big galaxies that we see in our universe today. So then you add some more dark matter, and some more dark matter, and some more dark matter. Eventually, you have to add enough dark matter that the gas collapses fast enough that you can actually form big galaxies and big galaxy clusters, until you finally end up with a simulation where there's a bunch of galaxy clusters the way that we actually see it in our actual universe, right? What are we trying to do here? We're trying to create a computer simulation that accurately reproduces the universe that we see ourselves living in from telescope images. And in order to create a universe that actually looks like ours, you need to add a lot of dark matter. So apparently dark matter is not a new phenomenon. It has been there, influencing the evolution of galaxies from the very beginning. So dark matter sounds like a crackpot theory, right? Dark matter sounds like a bizarro conspiracy theory, right? That there is a lot of extra mass in our galaxy, but you can't see it in telescopes, right? It doesn't give off light. It doesn't absorb light. It's transparent. It's this spooky stuff floating around the galaxies, pulling everything together, but we can't see it. Sounds crazy, but it's the best answer we've got, right? All of our evidence is telling us our understanding of gravity is okay, right? Einstein's theory of gravity seems to be working just fine. So apparently, yeah. I'm not saying that Einstein's theory of general relativity is the absolute answer, because we don't know that yet, right? Tomorrow's a new day, right? A good theory should be falsifiable. A good theory should be able to be disproven if you have the right evidence. What I'm saying is, all the evidence today seems to be indicating there's nothing wrong with our understanding of gravity. The problem is that the universe is just filled with this gas floating around in between the stars, floating around in between the galaxies. It's everywhere, and we can't see it in our telescopes. That's the current state of the art. That's what we know today. right? Right. The thing I forgot to say. When I said before that in order to explain the evolution of the universe, you need to add a lot of dark matter to your simulation. When I said a lot, I mean a lot, right? All of our current measurements indicate that there needs to be about 5 times as much dark matter as there is normal matter in order to explain our universe, in order to explain everything we see, in order to explain the rotation curves of galaxies and the motion of galaxies in galaxy clusters and the gravitational lensing and the... Oh, we're getting a little bit of rain. You're probably hearing that on the microphone. And the formation of the very first galaxies, right? In order to explain everything that we're seeing in our universe, you need a universe where there's 5 times more dark matter than there is normal matter. What? What? This stuff, right? This is a big mystery in astrophysics, right? That apparently our universe is filled with this dark matter. We can't see it in our telescopes. We can only see it, how do we know dark matter is there? We can see it from the gravity that it exerts. We can see dark matter. We can see dark matter from the effect that its gravity has on visible matter, on the stuff we can see. Stars, galaxies, gas. So what is the stuff? What is dark matter? The short answer is we don't know, right? At this point, people have been arguing about dark matter for decades, and we've thrown out a lot of ideas. People have been throwing around a lot of ideas, and you investigate those ideas, and they don't work, right? People have thrown out lots of hunches, lots of guesses as to what the dark matter could be, and so far, they've all been disproven. So what we're left with today is our best, so take this with a big grain of salt, our best guess for what dark matter is some kind of weakly interacting massive particle, or what's called a WIMP. All right, the name WIMP it's a joke, right? They were intentionally being cheeky when they named this because it's very strong, right? Dark matter is very strong, so let's call it a WIMP. But what is a WIMP, right? A WIMP it's a weakly interacting, right? Meaning the particle only interacts through the weak nuclear force. But it's massive, so it interacts with gravity, right? It's some kind of exotic particle, right? Dark matter must be some kind of exotic particle that has no electric charge. It's neutrally charged, right? Because if dark matter had an electric charge, it would interact with light, and then we'd be able to see it. It doesn't interact with the strong force, because if dark matter interacted via the strong nuclear force, we would see it in particle detectors and nuclear reactors, and we don't. It should interact with the weak force, because everything does. That's a bit of an assumption, but it's a decent assumption, right? We think it'll interact via the weak force, we think. And it needs to have a large mass because it's exerting a heck of a lot of gravity. That's where we're at today, right? Every particle that we know of that meets these criteria has been disproven. There aren't enough, right? Every particle that we think could be the dark matter, we've made the measurement. We've said, are there enough of those particles in the universe? And there isn't. So that's why I said a minute ago, the dark matter is some kind of exotic particle. Exotic, by which I mean we aren't sure that it exists. It only exists hypothetically, and we still haven't found it, right? It's not every particle in the standard model of particle physics. The particles that we actually know exist, they've been ruled out. So whatever the dark matter is made of, it must be some kind of particle that's out there in the universe. There's a heck of a lot of it, and we don't, I mean, as of right now, we don't know what it is. And we haven't seen direct evidence of it in our particle detectors. People are looking. There are experiments going on right now to try to do a direct observation, to see a dark matter particle run into the particle detector. And then we could all jump up and down and say, Eureka, we found one. One dark matter particle. But that would be a very big deal. That will be. I'm an optimist. That will be a very big deal when we finally do it. And there actually have been a few experiments that have gotten maybe a detection. And when I say a few, I mean like a handful. Like there are a handful of data points in a few particle detectors scattered around the world that might have seen a direct detection of a dark matter particle of some kind of WIMP. But not enough yet to really jump up and down and say we've answered this mystery. As of right now, that's what we know. The dark matter is real. That much we know. There's a lot of it. There's 5 times more of it than there is of us. And it's probably some kind of WIMP particle. We just don't know what kind. But we're looking. Okay? Okay. That's a lot. Let's take a deep breath and talk about dark energy. Because dark energy is a completely different topic. So put aside what I said about dark matter for a minute, all right? Clear your mind. Dark energy is something entirely different. Okay? This graph here is kind of a different way of drawing a Hubble diagram, right? This is a graph of the average distance between galaxies. So in other words, the vertical axis here is a way to measure the size of the universe, right? As the universe gets bigger and bigger in size, the expansion of the universe carries the galaxies further and further apart from each other, and so the distance between them gets larger. All right? The horizontal axis here is time, right? And here, at time zero is right now, and so as you look from there to the left, you're going back into the past. From there to the right, you're looking into the future. Okay? Okay. These 4 curves are 4 possible universes that we could be living in, right? So let's play a game, right? What sort of universe do we live in? Well, let's think about this, all right? I said a minute ago, the history and the evolution and the destiny of the universe are dictated by the fight between 2 forces. The expansion of the universe is trying to push everything apart. Gravity is trying to pull everything together. So who's winning? Well, if we lived in a universe where gravity is stronger than expansion, then eventually gravity will... So here's the Big Bang, right? Where this curve hits 0, that would mean, why are the galaxies 0 distance apart? Because they're all together at the Big Bang, right? So there's the Big Bang, the universe is expanding, but the expansion of the universe is slowing down because gravity is trying to pull the galaxies together. Eventually gravity slows down the expansion of the universe until the universe comes to a stop, and then gravity pulls all the galaxies together until all the galaxies crash into each other in a giant big crunch. Right? The big crunch is the cheeky name for when gravity pulls all the galaxies back together so that's what we call a recollapsing universe. A recollapsing universe is one where gravity is stronger than expansion and gravity will eventually pull everything back together. All right? So a recollapsing universe is where gravity is stronger than expansion. The accelerating universe here is one where expansion is much stronger than gravity, and therefore expansion is pushing the galaxies apart faster and faster and faster. So this graph isn't a straight line, Why? Because the expansion is actually speeding up. Expansion is stronger than gravity, so much stronger than gravity that that the universe is, or that the galaxies are actually getting farther apart faster and faster and faster. This coasting universe is one where expansion is stronger than gravity, but to the point that gravity is essentially negligible. Right? If you imagine a coasting universe is one where the Hubble constant is a constant, the universe is expanding at a constant rate, and this graph is just a straight line. Basically, what if gravity were negligible? You can just ignore gravity, and the universe is expanding at a constant rate, and therefore this graph is just a straight line. So, as if the galaxies were coasting at a steady speed away from each other. Or, to be more honest, as if the Hubble constant, as if the expansion rate of the universe were just cruising steadily, carrying the galaxies apart at the same rate forever. This critical universe is one where gravity and expansion are perfectly in balance. Right? A critical universe is one where there's just enough gravity in the universe to slow down the expansion of the universe, but never actually bring it to a stop. Right? So notice this green line is bending down, right? The expansion rate of the universe is slowing down, but it never actually comes to a stop, because if the expansion of the universe came to a stop, then gravity could bring it into a recollapse. Okay? So, 4 possible universes. One where gravity is stronger than expansion, one where expansion is stronger than gravity and speeding up, one where gravity is other way around, right? A recollapsing universe is one where gravity is stronger than expansion. And a coasting universe is one where expansion is stronger than gravity and staying at a constant speed, a constant expansion rate. An accelerating universe is one where expansion is stronger than gravity and it's speeding up. And then a critical universe is one where expansion and gravity are perfectly canceling each other out, perfectly in balance. Where in a critical universe, the universe keeps on expanding forever, but it's constantly getting slower and slower and slower and slower and slower, but never comes to a stop. All right. So these are 4 possible universes. Which one do we actually live in, though? Let's look at the data, right? Because these gray data points are the distances from type 1a supernova. Right? In this, here we've got at different distances, right? Because here we are right here. Oops. Nope. Oops, sorry about that. All right. We can actually plot, right, where these galaxies are from the distances that we get from type 1a supernova. And the first thing you'll notice is it's definitely not red, right? These data points do not match a recollapsing universe. We do not live in a universe that is going to come to a stop and then recollapse. There will not be a big crunch. All right, so once we've ruled that one out, which of these 3 is it? And you'll notice the data kind of fits these other 3 pretty well. But it definitely favors the orange line. Right? These are the error bars, right? These are the data points, and then you'll notice these horizontal gray lines they're the uncertainties. You could conceivably think, oh, okay, the data fits the blue line okay, fits the green line okay, but man, it sure looks like, from the best data we have today, that we're living in an accelerating universe. That where the expansion of space-time is pushing the galaxies apart. What's causing the galaxies what's causing the expansion of the universe to speed up? That's what we're calling dark energy. All right? Dark energy is this name that we're giving for this energy that exists in empty space, because of course, as I've said before, and I'll say it again, right? Empty space is not actually empty, right? Empty space is made of space-time. And that four-dimensional space-time can stretch, can expand, and apparently it can expand at a faster and faster and faster rate, because that's what we see from the data. Right? Dark energy is essentially this anti-gravity, right? It is this energy that exists in the fabric of the universe. It's an energy that exists in space-time itself. And it is this energy that is welling up out of space and pushing the galaxies apart, pushing space-time to expand faster and faster and faster and faster and faster. Again, we call it dark energy because we don't have a better name for it. We call it dark energy because we're in the dark about what it is, where it comes from, why is there dark energy in space-time. People are still working on it. We don't have a good answer yet. Where does the dark energy come from? Where is it going? We don't know. But from the best evidence that we have, from the present going all the way back to 10 or 12 billion years ago, it sure looks like the dark energy has been there, and we've been living in a universe that was accelerating. It sure looks like from the very beginning. And here's the thing. What I just said. Where is the dark energy? It's in space itself. That space-time, the fabric of reality, right? I called it earlier, right? That space-time is the game board on which the game of physics is played, right? That space itself has this dark energy, and that dark energy is driving the expansion of space-time to happen faster and faster and faster. Which means, since dark energy exists in space, and there's a lot of space in the universe, there's a lot of dark energy in the universe. When you add up all of space itself, the dark energy seems to make up, when you do the math, you total it all up, the dark energy constitutes 73% of the universe. If you add up all of the matter and energy, because of course matter and energy are just the same thing, right? Mass is just another form of energy, right? When you add up all the matter and all of the energy, when you add up everything in the universe and you add it all up, because there's so much space in the universe, there's a lot of dark energy in total. And that the dark energy makes up 73% of the universe. Dark matter is 23% of the universe. And everything else, everything that we actually understand, everything that we actually know exists and that we can see with our eyes and with our telescopes, that adds up to 4% of everything in the universe. Protons, neutrons, electrons, photons, neutrinos, right? Everything in the standard model of particle physics, all the normal matter that we understand, adds up to 4%. 23% is dark matter, of which we don't know what it is, but we think it's some kind of exotic WIMP. The other 73% is dark energy. It's everywhere. It's in space. And we don't know what it is. Dark energy is the biggest mystery in astrophysics because it's a part of our universe. It dominates our universe, and we only have the vaguest idea of what it is or where it comes from. And yet, it is going to dictate the fate of the universe, right? we don't live in a universe that's going to recollapse. We don't exist in a universe that's slowing down or coasting. We exist in a universe that started in a big bang and is expanding faster and faster and faster and faster and faster, and the galaxies are just going to get red shifting away from each other. The galaxies are just going to speed away from each other ever faster forever. We don't know exactly why, and we don't know exactly what the dark energy is that's driving this, but to the best of our data, to the best of all of our measurements today, the ultimate fate of the universe is one where every galaxy is just off on its own. Right? That the universe, that space has expanded every galaxy away from every other galaxy until every galaxy is just off on its own. A 100 years ago, a little over 100 years ago, astronomers would look out at the Milky Way, and they thought that our galaxy was it. They couldn't see that far. The other galaxies in the universe were these faint, blurry smudges in their telescopes. People 100 and some years ago, they thought that our galaxy was the only galaxy in the universe. They thought that our galaxy was this island of stars and gas in an otherwise empty black universe. So that when it was discovered that those blurry smudges in their telescopes were actually galaxies unto themselves, and that there were a lot more galaxies than just ours, and then all of a sudden everybody realized that the universe was a lot bigger and a lot more populated with stars and galaxies and nebula and who knows, people, than we used to think. It was a revelation. We're living in a golden age of the universe, right? It's a good time to be here in the universe because the universe is old enough that we can be here, right? Our universe is 13.7, 13.8 billion years old, and that has been enough time for 3 generations of stars to be born and the chemical evolution of the universe to have happened. Our universe is old enough that enough metals have been created that some of those metals could end up as the Earth and plants and animals and us, right? Our body is mostly made of metals. We couldn't have been here 10 billion years ago because the universe was too young and the metallicity of the universe was too low to make people out of. But also, it's a good time to be here because if we were alive, maybe not billions of years, but maybe hundreds of billions of years, if we were around in the far, far, far future, hundreds of billions of years from now, the expansion of the universe is going to have pushed the galaxies so far apart that they wouldn't be able to see each other anymore. Every galaxy is going to be so far away and its light is going to be so redshifted, you won't be able to see it anymore. Every star will be pushed beyond the cosmic horizon. If we were alive 100 billion years from now, we would look out at the universe and we would actually think that we were it. We would think that our galaxy was the only one. Because we couldn't see. The universe is infinitely large and it's probably full of infinite numbers of galaxies, but we couldn't see that. It's a good time to be here. Where the universe is old enough that we can be here, but that also the universe is young enough that we can still see our neighbor galaxies and they can see us. The ultimate fate of the universe is a little dark and sad. I mean, dark, metaphysically dark, but also physically dark because the galaxies are far away from each other and they're not shining on each other as very brightly. Um, yeah, the fate of the universe is one where every galaxy is off on its own. Until all the stars in that galaxy, right? All of the stars will burn out, right? Every star will live through its life cycle and fizzle out as a white dwarf or a neutron star or a black hole. 100 billion years from now, the only stars that are left will be little red dwarfs and little white dwarfs slowly giving off what heat they have left in an otherwise black sky. A little bit of a downer. There's a silver lining here, though, which is we don't know why the Big Bang happened the first time. Right? What created the Big Bang? What created the conditions of the Big Bang initially? Could it happen again? And that's the last lecture. Right? We're going to end this lecture with the ultimate fate of the universe. Cold and dark with the very long life. The only stars left are the ones that can live the very longest. We'll end this class talking about the beginning of the universe. What happened in the Big Bang? Why did the Big Bang happen? The short answer is we don't know. So I don't want to get your hopes up there. But we have some ideas. And the silver lining here is the end of the universe might not be the end. That the conditions that created the Big Bang in our universe originally may not be unique. It's probably rare, but it might not be unique. And if the Big Bang can happen once, maybe not, maybe again. So just because the fate of the universe as we understand it today, again, this is all based on the best data we have right now, take it with a small grain of salt, but the fate of the universe as we understand it today does not have to be bleak. Because, I mean, this isn't going to happen for, hundreds of billions of years, so it's not like not like we're all going to be there to witness it. If that's a good thing or a bad thing, take your pick. But the exciting thing is, let's look back and see, how did this happen the first time? How did this universe happen the first time? How did this Big Bang happen the first time? And that we've got some pretty good ideas about. And once you get a handle on how this whole universe happened the first time, then you can go to the next step and say, well, why not again? Why not again? Let's see. That'll be the topic for next time. All right. Have a good one, everybody.